In this short video, I just want to go through the point of division formula and show how we can get very similar triangles to help us to obtain the same solution for a certain particular situation. So let's suppose we have 3 points, A, B, and P. All three are collinear. They live on some sort of line segment. And suppose I'm given the coordinates A, which is say 1, 2, and let's make B say minus 1 and 4. Okay, and suppose you're given that the length of AB to the length of AP is 3 over 1, or AB is 3 times longer than AP. And our goal is to determine the coordinates of P. And so for argument's sake, let's let P be the x comma y. Let's be those coordinates. Okay, and we're going to try to get x and y, and what we're going to show is a couple of different ways to obtain the value of x and y. And there's 2 concrete situations here. One is we can assume, let's assume P is between A and B. Okay, that's an assumption that we're making. So let me try to plot A. A is, if A is right here, let's say 1, 2, then B is minus 1 up 4. It's over here, and here's B. And if this is 3 units long, then a third of the distance is P. Okay, and at this point, we want to make some similar triangles that help us obtain the value of P. Okay, and in each situation, I'm going to be using some sort of bigger triangle to help us. So here's a bigger triangle where the coordinates of this point right here has the same x coordinate of B, which is minus 1, and the y coordinate is the same y coordinate of A, so the coordinates here are minus 1, 2. Therefore, the length of this is the difference of my x coordinate here and here, which is 2 units. And likewise, the height here is the difference between my y coordinate, let me write that down, minus 1, 4. So the difference of my current y value, 4, minus my y value here, which again is 2. So I have an isosceles triangle. Okay. Now there's a couple different situations that we could do to get a similar triangle to this bigger triangle. Okay. Let's go through 2 different situations. So let me draw the picture again. So here's B, here's A. Let me make that bigger triangle. Let me put P here. Okay, and let's assume I do a similar triangle this way. So I'm going to relate the bigger triangle to this smaller triangle. Now, to get the right ratio of sizes here, this smaller triangle has a hypotenuse AP. And that hypotenuse AP must be a third of the size of AB based on the ratio that we have up here. So that means this line segment, a third of this is this length. And vice versa with the x, or the length of this leg. So that means the length of this leg right there has to be 1/3 of this length. Now, in terms of A and B, remember the coordinates of P, I used x and y. The coordinates of P, it has a y value of y, and that means the length here would be y minus the y coordinate here, so y minus 2. Okay, and we can solve for that. We add the 2 over, we get 2 plus 2/3, and 2 plus 2/3, we can say that's 8/3, so we get y is equal to 8/3. And that's a value that's a little bit greater than 2, but less than 4, kind of jives with our picture. Okay, now let's get the x coordinate. We know this length is 2, and we know that 1/3 of 2 must be this difference with this unknown x. So to get this length here, we're going to subtract the x-coordinate of A, which is 1, from the x-coordinate of P. So I have 1 minus x. Now solving for x, let me add the x over and subtract that 2/3 here, and we get x is equal to 1/3. So that means we find out that the point P is 1/3, a third upon using these similar triangles. But that's just one particular picture that we could use. So let me use a different situation here. Okay, let me again draw the same picture. Okay, I got AB, and I'm going to put P here again. Let me draw the bigger rectangle, or sorry, bigger triangle. Okay, and instead of doing as we did before with this triangle, I'm going to make another one up here. So let's relate this triangle to the bigger triangle. Now, if this length was 3 units long and this length was 1, then this length must be 2 parts of the 3. So that means this triangle here is 2/3 the size of the bigger one. And we can play the same exact game. We know that this length, which again is still 2, well, I'll do the y coordinates first. We know this length, which is 2. If we take 2/3 of that, that must equal to the length involving the y coordinate of P. And so we take the difference of the y coordinate with B and from the y coordinate here of P, so we get 4 minus y. Okay. And if we solve for that, if you look what you have, you add the y over, subtract over the 4/3. Let me do this in 2 parts. So we have 4 minus 4/3. This right here is 12 over 3, and so we get 8 over 3, which is exactly what you got over here. Okay, that's a feel-good moment. Now let's do the same thing with the x-coordinate. This length is 2. 2/3 of it is this length. So 2/3 times 2. And if I involve the x-coordinate here and the x-coordinate here, that's x minus the x-coordinate of B. So I have x minus a minus 1, that's plus 1. Okay, so that's x plus 1. You subtract over 1, I have 4/3 minus 1, and you get, lo and behold, x equal 1/3. So we get the same exact solution. But that's not the only set of triangles you could use. We could yet do a third approach. Okay, so I'm going to draw the picture. I'm running out of room here. So here's A, here's B, here's P. Okay, I'll do this bigger triangle, but actually not the triangle I'm going to do the similar triangles with. What I'm going to do is, here's a triangle right here, and then here's another triangle right here. I'm going to relate those two to each other. They have to be similar. And we know the ratio of the hypotenuse is 2 to 1. Okay, so that means this triangle is 2 times bigger than this triangle. Now this one you're going to have to do this one you have to work a little bit more because you're going to have to relate this side to this side, and it's going to be a little bit more complicated equation. So let me put it down here. But this length right here is still going to be the y coordinate minus the y coordinate here. So I have 4 minus y, but it's 2 times bigger. It's 2 times bigger than this difference. And so this would be y minus 2, so y minus 2. Now let's expand everything. Okay, we have 4 minus y. We have 2y minus 4. Let me add the y over, so you get 3y. Let me add the 4 over, you get 8, and you see you've recovered y is equal to 8/3. Okay, and we can do the same thing for the x coordinate. You can say, well, you know, this one right here is the x coordinate subtracted with the x coordinate here, and so I have x minus a minus 1, so x plus 1. I know that's twice the length of this one, which is the x coordinate of A, which is 1 minus x. So 2, 1 minus x. We get x plus, we're going to expand everything. X plus 1 is 2 minus 2x. Let me add that 2x over, you get 3x. Let me subtract the 1 over, you get minus 1. And, oops, sorry, plus 1. So because 2 minus 1 is that. And then we get 1/3. And we get the same exact solution. So for one particular situation, there are 3 different similar triangles that you could use to help you to be able to determine those coordinates. If we look in the textbook in this problem, it is assuming that you are using a particular set of triangles. It's going to be just this situation only here. So it's very important that we have a drawing and we recognize what set of triangles that we're doing and then make the proportion accordingly. But now I said in the very beginning, this was only one situation. Okay, and I'll get another video to show that one.